Hello, this is Andy Schweitzer and a second in a series of videos on enthalpy. A couple things we'll look at is the mathematical calculations of enthalpy and then what we can do with the enthalpy. Just going to run through a little example of how it works, what it means. Okay. When we have a reaction, let's just say, and I could really use any reaction that we would like. But let's just pick a burning reaction. We know most burning reactions, or all burning reactions, are exothermic. So I am going to pull up a table of values. Here we go. And we could pick something to burn. We could even burn a diamond, but let's burn something else here. Let's burn methanol. I use methanol a lot. So I'm just going to copy this on here, and these are the values. First is delta H, delta S, and delta G. So either way, let's do that. I know I have those values, and let's flip back to my page. All right, so methanol is going to be, I'm going to print that right here so I have it for a moment. Okay, so methanol is going to be CH3OH plus O2 yields CO2 plus H2O. Balance-wise, one carbon, 4 hydrogens, so I'd put a 2 here. 2 and 2 is 4. I can't get 4 there, so I'll go 2 and 2, and then this flips to a 4. 4 plus 4 more is 8. 2 times 1 is 2, and then I need 6 more. 3 there gives me 6. Alright, so that means every time this reaction runs through 2 of these, 3 of these, I get 2 of those, 4 of those, and some amount of energy. Alright, that energy would be described as delta H. Delta H would be negative. But what is that value? We'll find out in a moment here. Okay, so one thing you should note that is I want to figure out the amount of energy that's involved here. If I could somehow measure the total energy involved in the reactants and take the total amount of energy involved in the products, just subtract those, to the difference would be the amount of energy that's going to be released. Unfortunately, it's difficult to tell how much energy is actually in each of these pieces. So this would be a way we do absolute energy. Okay, that's difficult to do. But if we could, that'd be a very good way to do it. Simply say how much total energy is involved in this thing, and then just simply subtract the two, and away we go. All right. Now, what we generally do is the product minus the reactants equals your change in energy, or change in delta H in this case. All right. So heat energy. Now, since we can't do total energy, anytime we have a hard time measuring something, we generally do what's called a relative scale, which means that if I can measure the total energy of the reactants from some common measuring point, and then measure the energy of the products from that same common measuring point, then the difference between these 2 points would be the amount of energy, the difference. In this case, the reactants are very much higher in energy than the products are. Another example of this would be this particular energy profile, like that, where my reactants are much higher in energy, than therefore subtracting the two gives me my difference in energy, or delta H. So it's difficult, but any way we can measure these energies the same, then we just subtract the two. And what this is called delta H of formation. And they put a little F here into that. And again, this is just describing how they collect their data. So what they say here is, okay, well, if I have carbon, hydrogen, and oxygen in those elemental forms, how much would it take for me to create, with carbon, hydrogen, and oxygen, to create the substance of CH3OH and O2. I need 3 of those and 2 of these. And they say, okay, well, if I have carbon, hydrogen, and oxygen, okay, individually, how much would it take to make some carbon dioxide and some water? Of course, I have 2 of these guys. I'm making 4 of these. So again, the quantities matter. That is what delta H information says. Okay, and you can go to your charts and which is thermodynamic tables, and it basically tells you. Okay, so take a moment, and I'm gonna do delta H for this guy. I'm gonna rewrite my equation just so I can see it here. CH3OH, 2 of them, plus O2 yields CO2 plus H2O, and I do believe the balancing was 3, 2, 4. So 3, 2, 4. Now, to get your delta H values, okay, just go to your chart and look them up. Now, I wrote that the methanol already was negative 238. I'm just going to use to a tenth, or to this whole number, negative 238. Okay, it's in kilojoules per mole. That means it takes that much energy to go from carbon, hydrogen, oxygen to this guy. All right. Now that's for 1 mole. I'm using on a 2 mole basis, so I'll need to double that eventually. But let's find our other values. I need oxygen, and it's going to be right here. So just roll through your chart. This is one I provide in class, but oxygen is going to be coming up here. There's O2. It says 0. And the reason why it says 0 is because we're doing a comparison basis from elements, use my marker instead, from O2 to get to O2 doesn't take anything. So the O2, any element is 0. Whenever we're on a formation-based, elements should be 0. All right, and this is carbon dioxide gas. I'm going to go water. I'm going to do it in the gas phase as well. I believe it burns. It would probably be gas. So carbon should be a little higher, and there's the carbon. No, that's copper. And pass I did. It is right here. It is negative 393. All right. No more yet. This is going to be negative 393, and then H2O as a gas. It's either going to be hydrogen or oxygen. Here's hydrogen gas, negative 241. Not H2O2, H2O, and it must be a gas, negative 241. All right, so negative 241. So this is on a per mole basis. So I'll need to take all these guys and multiply them by their values here. So 238 times 2 equals a negative 476 kilojoules per mole. And I'm not going to write all the units in there all the time, but 393 times 2 is 786. And this is 241 times 4 is 968. Sometimes the hardest part about this is just keeping track of your numbers, being clean, not making any clerical mistakes. Again, I want to add up all the energy from my product reactants, all the energy from my products. And that's how I'm going to compare the two, because energy is conserved by the first law of energy. All right, so this side's pretty simple. It's just a negative 476. I'll put that right here. This guy is going to be a little bigger. Again, this is going to be a negative. Both of those values are negative. 786 plus 968 equals a negative 1754. Now the difference between the two, just so we're all on the same page, we go delta H of the reaction equals the sum of the delta H of the products minus the sum of the delta H of the reactants. Well, crooked was there. So it's going to be a negative 1754 minus 476. Alright, so if you subtract those two values, you get a negative, grab my pen here a second, a negative 1278 kilojoules. Now, it won't say kilojoules per mole because I use different amounts of moles in each of these individuals. Well, what it means is that every time this reaction cycles through one time, that requires 2 moles of this guy, 3 moles of this guy, 2 moles of this guy, and 4 moles of this guy, I get a whopping 1,278 kilojoules of energy. Okay, so there is one type of mathematics, that question that they often ask, and it would be this. All right, if I were to run 2 moles of methanol through this reaction, how much energy would I get out? Well, assuming excess oxygen, I would get 1,278 kilojoules of energy. What if I ran 50 grams of methanol through? CH3OH. This is again just a linear mathematics. Okay, I would go 50 grams. Now, of course, this is on a per mole basis, but get rid of the grams and go to moles. And 1 mole of methanol weighs, okay, 12. I got 3 more there, 16, plus another 1. Add all those up. 12 plus 3 plus 1 plus 16 plus another 1. I think that's what it is. I think it's 32. All right, so 32 grams. So that's not quite 2 moles. 50 divided by 2, 50 divided by 32 is 1.56 moles. Of course, it's just a simple proportion that if 2 moles gave me this much energy, how much would 1.5 give? Simple factor label, get rid of moles, and go to kilojoules of energy. 2 moles gives me 1,278 kilojoules of energy. And I'll do that math here, times 1278 divided by 2 is 988. So again, 2 moles gives me this, so I only have 1.56, so it should be less than that value. That number to me makes sense. 998 kilojoules of energy. Now the negative simply means that it is being released to the surroundings. It is exothermic. Okay. All right, so all of that is the delta H and its calculations. Let's look at the next one, which is going to be, well, let's stop there for that calculation of delta H. Okay, let's just kind of review for that moment. This is our main equation. You will find it is the difference between a difference. Again, this first little triangle here, this delta sign, is referring to the actual value itself. What's the difference between oxygen and oxygen? Well, it's nothing. What's between these elements and all its individuals? Well, okay, well that's negative 238. That's that value. And then we add all of them up to get the total energy of the products, total energy of the reactants, and this subtraction is the subtraction between these two, giving us our delta H. A negative delta H, of course, is a exothermic reaction, and a positive delta H would be an endothermic reaction. Thank you very much.